All right, welcome back to The Explainer, first-year organic chemistry students. If you're staring at a giant web of chemical reactions right now and wondering how you're ever going to keep them straight for your upcoming exams, well, you are in exactly the right place. Today, we're putting a sharp focus on completely demystifying the functionalization of diazonium salts. We're going to build a comprehensive study guide together that doesn't just show you the what, but really digs into the how and the why behind synthesizing haloarenes. By the time we wrap up, navigating these complex pathways is going to feel like second nature to you. Let's get into it.
Okay, let's dive into this. Here's our syllabus for today. First, the diazonium starting line. Second, Gattermann reaction pathways. Third, the role of copper. And finally, comparing synthesis methods. Starting off with Section 1, the diazonium starting line. Meet the protagonist.
Now, before we actually define the reaction itself, we really need to meet our molecular protagonist, benzene diazonium chloride. I want you to think of this molecule like a tightly coiled spring. It's absolutely primed for transformation, mostly because it's holding on to a nitrogen group that is just desperate to leave as nitrogen gas. But, like any coiled spring, it needs exactly the right trigger to release that energy and bond with something new. So to set the foundation for your notes, let's clearly define that trigger. The Gattermann reaction is a regioselective aromatic substitution method used to prepare haloarenes from benzene diazonium chloride. What does that mean in simpler terms? It's basically a highly specific chemical method for kicking off that impatient diazonium functional group and replacing it with a halogen nucleophile, like chlorine or bromine. It's a beautifully elegant molecular swap.
Moving on to Section 2, Gattermann reaction pathways, the visual map. Let's actually see how this builds into the real chemical pathways that determine our final target halogens. We know what we're starting with, and we know our ultimate goal is to attach a halogen, and this brilliantly illustrates the heart of the reaction. Take a look at the left side. There's our coiled spring, benzene diazonium chloride. Now, follow that top arrow. If we treat this with a combination of copper powder and hydrochloric acid, so Cu over HCl, we yield chlorobenzene plus our byproduct, nitrogen gas. Now follow the bottom arrow. If we instead use copper powder and hydrobromic acid, Cu over HBr, we yield bromobenzene, and again we've got nitrogen gas bubbling away. The main takeaway? The copper sets the stage, but the acid determines your final product. Okay, so the crucial contrast between Path A and Path B is a classic exam trick. Honestly, professors love testing this, so pay close attention. The required halogen acid must strictly match your desired aryl halide. If you want chlorobenzene, you absolutely must use HCl. You want bromobenzene, you must use HBr. Oh, and don't forget the tiny triangle you saw on those previous arrows. That is the delta symbol, and it represents thermal energy. Because this reaction, it requires some serious heat to pop that nitrogen off. Which brings us to Section 3, the role of copper under the hood. So we know heat and acid are involved, but what exactly is that metallic copper powder doing in the mix? Let's zoom into the atomic level here and look under the hood to explain its exact mechanical role. Here is the step-by-step molecular journey of the diazonium group being replaced. First up, we have thermal decomposition. The heat basically starts to loosen things up. Then comes the real magic, the single electron transfer, or SET. I want you to think of the copper powder like a very exclusive bouncer at a club. The copper hands out a single VIP ticket, which is one electron, to the diazonium salt. This creates a radical intermediate. That single electron entirely destabilizes the nitrogen, kicking it right out the door as N2 gas, and leaving an empty VIP booth for the halide nucleophile, so your chlorine or your bromine, to just slide right into the aromatic ring. So the crucial point is that finely divided metallic copper is the engine of this entire process. It is not just a passive bystander. It actively drives the single electron transfer process that makes the nitrogen evolution and nucleophile entry possible in the first place. Without that metallic copper powder handing out the electron, the reaction just wouldn't proceed the same way. All right, Section 4, Comparing Synthesis Methods, the Ultimate Study Guide. Now, you know how it is in organic chemistry. You are rarely tested on just one reaction in a vacuum. You're tested on whether you know which reaction to use in a specific scenario. So let's build the ultimate study guide to help you easily distinguish these on exam day. The absolute most common mix-up is between the Gattermann and the Sandmeyer reactions. They literally do the exact same thing, turning diazonium salts into haloarenes, but their defining procedural difference is the catalyst. Gattermann uses metallic copper powder, Sandmeyer uses cuprous salts like CuCl or CuBr. So why does this matter? Well, Cooper's salts provide both the copper catalyst and the halide nucleophile in a single homogeneous package. This makes the Sandmeyer reaction significantly faster and gives you a much higher yield than relying on a solid ground-up metal powder. To lock this in, here is a super handy mnemonic device. S for Sandmeyer uses S for salts. G for Gattermann uses G for ground-up metal. Just remember that, and I promise you will never mix them on a test. To pull it all together, here is your high-yield summary table for quick reference. Honestly, feel free to pause and screenshot this right now. Up top, we have our Gattermann with copper powder targeting chlorine or bromine. Then we have our Sandmeyer with Cooper salts, also targeting chlorine or bromine. But look at the bottom row for a second, the Ball's-Schiemann reaction. This one is unique. If your exam asks you to synthesize a fluorobenzene, you cannot use Gattermann or Sandmeyer. There is no way around it. You must use the Ball's-Schiemann reaction, which utilizes fluoroboric acid specifically to target fluorine. You know, learning how to navigate these intricate chemical pathways is exactly what transforms you from someone who is just memorizing a textbook into a true analytical chemist. The concepts we've covered today, from understanding those single electron transfers to choosing exactly the right catalyst for the right yield, these are the sparks that ignite higher-level scientific thinking. Seriously, you are well on your way to mastering organic synthesis. Before we go, I want to leave you with a typical exam scenario to test your conceptual understanding. Imagine you are standing in the lab. You need to synthesize chlorobenzene, and you have a strict requirement for the absolute highest yield possible. But you look in the cabinet and you only have hydrochloric acid and finely ground metallic copper powder. So what do? Do you proceed with Gattermann, knowing it might be a bit less efficient than Sandmeyer? Or do you halt your synthesis entirely to order Cooper salts? Think about how the available reagents really dictate your pathways. Keep synthesizing this material in your mind, and you are going to be more than ready for whatever organic chemistry throws your way. See you next time.